Hello, class. I always love the first lecture in the morning, although the last couple mornings it's been a difficult lecture sometimes to prepare everything and get everything set up. Today, we're going to look at we're going to finish out thermal stresses, and I'm going to do an example problem that I haven't even put together yet, but it's along the lines of what I mentioned to you yesterday, where we're going to place a bar between two rigid surfaces. And in fact, I'll draw it out here for you. I've got a aluminum bar, right? So we're going to change it from steel so that you can get a little more experience with other metals just than steel, and look at the characteristics of other metals too. Aluminum has one of the greatest coefficients of thermal expansion of any metal, really almost of anything. I'm trying to think of there's one thing that has a coefficient, lead. But lead is not a strong material. So if I was to, let's say that what we've got here is a prisoner, right? A prisoner's inside a cell, and he's thinking to himself, hey, you know what I brought back from the machine shop that I'm working in is this piece of aluminum, right? And the distance between the bars, what would be the distance between the bars? 6 inches, let's say, something like that. Well, we want to turn it into, so let's say 15 centimeters, which isn't quite 6 inches, but we'll say that the distance between those prison bars are 15 centimeters. And that's why you didn't take the steel bar back, right? Because the steel bar has half the thermal expansion coefficient of the aluminum bar. Or maybe it's not even an aluminum bar. Maybe it's something that has the same coefficient as aluminum, but is not steel. It's a ceramic. So you could get through the, prison security system with the thing. Anyway, we're saying it's aluminum. And we also know that the aluminum coefficient of thermal expansion is going to be 25, and that is literally more than twice what steel is. 25 times 10 to the minus 6 meters per meter degree Celsius. Now, when you look at the coefficient of thermal expansion, oh, you know what I forgot to do? I forgot to turn my timer on. Just a second. Okay, we're back, and the timer's on, and I set it for like 2 minutes less than I normally would have. But anyway, let's get back to this. So we're as prisoner in a prison cell. We're trying to expand these bars out, right? So we would have to think about, well, if this expands it, if I can heat this up, let's say I've got a little Bic lighter or whatever in my thing too. So I can heat this up, and that will expand it out. How much could I heat that up? Let's say 200 degrees Celsius. So delta T is going to be 200 degrees Celsius. Wow, I don't even know how you would need some fire device to heat that up, but you could actually get it hotter than that. If you had a little just like a brazier that they use on a barbecue, to sort of braise beef or whatever, just one of those things that you could turn on and heat that bar up. Let's say that you could get it to 200 degrees. All right, so what we know is that the strain in the x direction then is going to be 200 degrees Celsius times 25 times 10 to the minus 6 per degree Celsius. Let's just put that, you know that it's really meters per meters extension over original length meters. That's what it originally was, right? So we've got that heated up 200 degrees Celsius. Again, you'd have to find a way to obviously to do that, and that's why they don't allow heating devices probably inside your cell in a prison, and why would they, right? So if we do that, we end up getting a 0.005 strain in the x direction. Of course, there's no units because it's strain. So what we want to really find out is we want to find out what is the extension that this is going to push these two bars apart so that we can squeeze through there. We can't get through 15 centimeters, but maybe we can slim down and get through something that's a little bit wider than that. So right now we know that those are 15 centimeters apart, so 0.005 strain, right, times the distance that we have, 0.15 meters. And again, I can't stress the fact enough that when you go back to multiplying things, you should always, you know, refer to the primary units. Don't put centimeters in there. Put meters in there. Make sure everything is all of your dimensions are correct. So 0.005 times 0.15 gives me 0.00075. I'm gonna write it like that: 0.00075 meters. And the reason I wanted to write it like that was, what is that? Is that 7 millimeters? Is that 7/10,000? So no, of course not, right? That's 750 microns. That's how much that's going to push it apart. Or about 0.75 millimeters. That's why you know that this would never work, would it? Right? It would never work. That's right. Even though they do it in the movies for some reason. Although I think they had something where they crank that apart, and you could probably do something like that. But no, using heat to even heat this up to try and get out of there, even with aluminum, which is one of the highest thermal coefficients out there, is not going to work, right? Because it's just going to push it apart a millimeter. It's just going to expand a little bit. So that's not the case. And so I wanted to do that. But one thing that we haven't really looked at is, now that it has expanded, let's say that these are rigid surfaces. The bars aren't going to expand at all. This is going to heat up, and I heated up 200 degrees Celsius. So it's going to give me an elongation of 0.75, or it's going to give me a stress in the aluminum of 0.005, right? So if I wanted to find out what the stress was in the aluminum, we know that it's just Young's modulus for aluminum, modulus of elasticity for aluminum. Oh, you know, I wanted to point out another thing. You know, G, I called it the shear modulus, but its real name is called the modulus of rigidity. You know, so if in the future you refer to it and you've never done the reading for this class, and you hear modulus of rigidity, you'll know what it means. That's right. Shear modulus, modulus of rigidity, same thing, G. And G is never as great a slope or as great a constant as E is. You know, I just want to put that relationship between E and G up there again. Let me just write that someplace here. Yes. So G, right, modulus of rigidity, is always going to be E divided by 2 times 1 plus Poisson's ratio, right? So always remember that relationship between the two. And you can see that even if Poisson's ratio was 0, which it would never be, it's going to be greater than 1, that still, that's E divided by 2, right? So it's always going to be less than 1/2. G is always less than 1/2 of E. So if you know what E is, you know, you can pretty much, using Poisson's ratio about 0.3 for the metals, especially face-centered or body-centered cubic metals, that would give you a good approximation of what it's going to be. Now, let's get back to this, right? So we know what the strain is, but we don't know what the modulus of elasticity is for aluminum right off the top of my head. So I'm just going to look that up for a second. Okay, for aluminum, E, I'll put it down here. E for aluminum is 27, that's a 7 gigapascals. I think I'm going to have to go to a new pen. This one's doing okay, though. Let's just see if we've got another one over here that looks like it's pretty good. How's that one? Oh, that looks real good. All right, so we know that that's it. So we can figure out the stress because this, right, this is L0. And I know you're saying, hey, well, you know, really this thing is allowing to extend and then we push it back to that. So shouldn't L0 be the extended version? And then this, no, because this is actually at this point, and then it's going to be extending, but it's not going to be extending, so it's going to be pushed back in. So we still use L0. The truth is that there's little difference. There should be little difference as far as the extension. I mean, what we're looking at is 750 microns, or 3/4 of a millimeter. So it's very little over the full 15 centimeters that this is expanding. So let's use Hooke's law, right? This is Hooke's law. Let's use Hooke's law to find out what the stress is in that thing. So stress is going to be 27 gigapascals times 750 times 10 to the minus 6 meters. No, not meters. Oh, wait. Oh, I'm sorry. No. Oh, no. I should always do these beforehand. 0.005. I just didn't do it because this one's so easy, really. And this is just a stress. It's just Young's modulus, or modulus of elasticity, times the strain, 0.005. So the stress inside that is going to be, wait, don't tell me. I get 135 megapascals. And that still is far under the maximum for the aluminum. So if somebody were in a cell and heated this up, they'd only get 3/4 of a millimeter. But it wouldn't fail the aluminum. The aluminum wouldn't be failing if it did. In fact, what would fail if this did extend was this. So these would be pushed apart, but they'd only be pushed apart by about a millimeter. So you're probably not going to escape unless you really needed that millimeter to get out between those two bars. All right. So this ends our thermal stresses section that we're going to be doing. And what I want to move into now is the derivation of our torsion formulas. Right? We've got two torsion formulas that I want to derive. We're going to look at how we got them, and then we're going to apply the two torsion formulas that I'm going to derive right now toward solving torsion problems. All right, so to do this, I really have to draw a torsion member. All right, so here's what I've got. I've got a circular, and almost all torsion bars are circular. I can't think of any reason why you'd not want to make them circular, right? Because that's probably not drawn too well, but if they weren't circular, then there'd be some places that are further away from the center than others. And as you can see here, if this is my axis that's coming out right in the center, no place on a circular cross section is going to be any further away from the center than anywhere else. Now, here's what I want to do. I'm going to pull up on this. I can do this one of two ways. Yeah, I'll do it this way. We'll rotate clockwise. So I'm going to put a force. I'm going to call that force P, right? And that force is going to start to rotate this. Now, up here, the reason I'm drawing this little box around it is to show that this is attached to the wall. There's no rotation of the left end, right? The left end is set in concrete, no rotation. So if I draw a line along the side of there, let's draw that line along the side. We haven't, before we ever apply load P, okay? So before we apply load P, I've drawn a line on the side. Now, what does that line look like after I have twisted this? So let's say that I've actually applied load P now, and after I apply load P has turned or rotated, right? That's P1, and then when I've applied, oh, that's P1 too. So P, or let's call it, no, we'll call it P1. So I've applied P1, and it's caused it to rotate a little bit, right? So now we've rotated through there. Let me draw another line because I've got two triangles. And I've drawn these larger than they would be. In fact, what we're using here is going to be the small angle approximation. So for small angles, and this is something that you'll use throughout your life in your derivations when you're out there working, is that the tangent of gamma, an angle, equals the sine of gamma equals gamma. All right? We've used that before. We're gonna use it right here too. We're gonna look at these as being small, but I can't really draw them super small because then you know, well, let's put a couple things on here. We've got two triangles now. So I'm going to say that this is R. I think everybody can see that. That's the radius of the thing. And this distance here is L, right? So let's redraw those triangles. Not to scale, but large enough so that we can see what all of the individual parts of those congruent triangles are going to be. All right. Now we know that this is R. That distance right there is R. This distance here is L. I will call this angle gamma, and I'll call this angle theta. Now, what's this distance right here? See how that has wrapped around there? That is my deformation or elongation, or it actually is a shear deformation. So I've got a shear deformation. So let's do a little algebra, right? So we know that the arc here, since it's very small, that arc is very small, that we can approximate the distance here as a straight line. We can say that straight line there and the distance are the same. So I know that this distance here would be R times theta equals that deformation, right? If we were looking at this as an arc, which we've got right here, and we're saying that arc and the segment that connects those two are the same. All right? So we're using this approximation for small angles. So R times theta equals delta theta. You know, for a small angle over here, we can say that the tangent, right, of gamma equals delta sub s over L. In fact, we really are using the same thing over here, aren't we? We're really saying that the tangent of theta equals delta sub s over r, right? And then we say, well, r times theta, because we know that this is going to equal theta. We're using the small angles approximation. And we know that this is going to equal gamma. Does everyone see that? So if I was to look at this, I would say L times gamma also equals delta sub s, right? So we've got two congruent triangles that have a common side, delta sub s, and we're looking at that arc right there, and we're saying that this arc, whether one of the two arcs, I'm going to exaggerate, right? So we're saying that that arc right there, this distance here, which is delta sub s, right, is going to be approximately equal, I didn't do that too well, to the segment, right, that I have between those two. That's all I'm saying. And so I'm drawing this not so much as an arc. And at small angles, the arc and the segment, right, very small angles, those would be the same, wouldn't they? I think everybody can see that. So at small angles, and that's what we're talking about, those two would be the same. So these two would also be the same. So what we can say is that L times gamma is going to equal R times theta. Okay? Everybody see all the connections that we've got here? All right, so if I'm looking at this and I wanted to, I've got this, I can solve this equation for gamma. So gamma is going to equal R times theta divided by L, right? And we know, so I'm going to call this step 1. We know that if gamma equals R theta divided by L, and my shear stress, and that's what we've got here, isn't it? It's pure shear, right? We're pulling up on this and it's twisting. So all of this is shear. There is no torsion. Nobody's pulling on this at all. We're just shearing it. So we know that the shear stress is going to be related to the shear strain by the modulus of rigidity, right? So let's just substitute in there for gamma what we had for gamma. So I've got G times, and then what is gamma? R times theta divided by L. Left myself a little room there while I was thinking. All right, so that's what we have. I want to sort of rearrange that a little bit. And I'm going to say that this is G times theta divided by L times R. All right? G theta over L times R. That's just the way that I want. And of course, what that equals is my shear stress, just going all the way back here. I just thought I'd put it at the end so that we can have, you know, an equation for the shear stress in these terms, right? Okay, now what I want to do is I want to look at that cross section. And I think I'm going to put the cross section down here. Now let's look at that cross section and let's see how that force P manifests itself when I've got a torque, right? So I've got my torque out there. And I know that, P, it's going to be that even though P is applied out here, that's the applied force, how is it being resisted? Right? How is that force being resisted? Well, isn't it the force is being resisted from the center in? So really I have P distributed from the center out, because isn't it dependent upon rho, the distance out, and each one of those resistive small forces is along that line, all resisting the applied force P. Right? Does everyone see that? So all of these small little forces here, dP, are working due to the stress that they've got inside this. And actually, when I go, the stress in the center, right, is 0 megapascals, right, in the center. So in the center, since R equals 0, the stress is 0. And as I go out to the outside, it gets larger and larger and larger. And that's total stress underneath, that total resisting force of the steel bar has got to offset the applied force P that we've put on the bar, right? So let's say that this is the resisting force, the black, and then I've got a force P that I've applied to it, right? So it wants to resist that force P being applied. And what's the equal and opposite resisting force or resisting force? So the resisting torque, we look at this as being the applied torque. So the applied torque, right, has to, unless this thing's rotating, and it's not, has to be equal to the resisting torque, doesn't it? Right? Moments have to be equal about that point because it's not spinning. Once I apply it and it's twisted, it stops. There's no more twisting. So it's in static equilibrium. So the moments applied have to equal the moments that are being resisted. I think everybody sees that from our earlier static equilibrium analysis. Okay, so if we're going to do that and figure out what the torques are, then the torque that's applied, or the torque that's resisting the torque that's applied, is going to be the distance, the distance to each of the small individual dPs. Let's just take each one of these, right, is dP, small dP. And what I'm going to do is I'm going to sum all of those from the center 0 out to the radius. From the center 0 out to the radius to figure out what that dP, how that's going to react. All right. So my resistive force is going to be all of those little small dPs from 0 to R at a radius rho times dP. I'm going to sum up all of those. I don't know, what rho is for each one of those dPs, but I'm going to do it. I'm going to sum it from 0 to R, and I'm going to sum all these individual little p's, and that's going to come up to the total torque that's applied, which is P times R, right? So we know my applied, where can I write that? My applied force is going to be equal to P times R. That's the applied force, isn't it? My resistive force is going to be all of these small little resistive stresses times the cross-sectional area, and I'm going to sum all of those from 0, that's 0, out to rho, or out to R. All right, does everybody see that? Now let's replace dP, right? Let's replace dP with what it is, one of these little things here, because we know that dP is just going to be the stress times dA. So if P right, equals shear stress times A, then dP equals shear stress times dA, right? Does everybody see that? I don't think, it's a problem. So here's my integral then from 0 to r of rho. Now let's replace dP with tau dA. I'm going to say it's a tau. Can't remember if it's a capital gamma or a tau, but it looks, I think it's a capital gamma, but who knows? So rho times tau dA. All right, so 0 to r. We're still doing our integral, and we're integrating from 0 to r, and we're integrating all of those so that we can get t. That doesn't look like very good r, but whatever. Now, what I want to do is I want to replace gamma. So originally replace dP with this. Now what I want to do is I want to replace gamma with what we had figured out before that gamma was, right? Here's gamma, and we figured out that gamma equals this, right? Now this r is really going to be rho in this case because we were actually looking at the at this point right here, right? But all along this, it's a linear relationship between the force dP and r or rho, right? So it's 0 in the middle, but it's maximum on the outside where rho equals a maximum, and the maximum rho is r. All right. Well, wait a second. Am I losing this a little bit? Just say, oh, you know what? I think my camera has tilted a little bit. Let me just let me move that back up. Well, that's strange. There you go. That's better. I think. Yes, I'm sorry about that. I hadn't noticed. This book's getting thicker, and so I think that shifts the camera up. Anyway, I think everybody can see what I've got down here anyway. You know, the applied torque equals the resistive torque. The total applied torque is just going to be the force P times R. I mean, that's what a moment is, isn't it? Right? Force times distance, perpendicular distance. That's my torque that's applied. We're looking at the resistive torque now because we know that each one of these in the cross section is just going to be a small little p as it works its way out. It's not uniform, is it? It starts at 0 and it ends at a maximum. And that relationship is going to be a linear relationship going out. That's what we found. So let's substitute in what we've got here. So it's still 0 to r. I've got tau, and what is tau? Right? Tau I'm going to replace with, let's put rho there. Rho times tau, and tau is g theta over L, right? G theta over L times rho. And we still need our dA. So that's the equation that we've got there. So T resisting is going to equal, let's see, let's put this all together now. G is a constant, isn't it? That's modulus of rigidity, so that can come outside of the equation. How about theta? Theta is our angle of twist, isn't it? And you know, after we've twisted it, that angle, aren't we going to stop there? Right, so that's a constant. The angle of twist is a constant. How about the length? Is the length getting longer or shorter, longer and shorter? No. The length is a constant as well. And so what this leaves us with then is rho squared dA. Where have we seen that before? We know that the integral of rho squared dA equals our polar moment of inertia, right? Equals our polar moment of inertia. Now I've just blocked those other ones out, so I should, you have to go back in time. That's L times gamma equals r times theta. And of course, we already left that behind a long time ago. So we know this is J. So what I really have is G times theta times J, which is the moment of inertia for area, or second moment of inertia of area, however you want to look at it, over L. What does that tell us? That gives us our first equation. Theta equals TL over JG. What I want to do is I want to put that down here, right? Theta equals TL over JG. And that is the first of two of our torsion equations. Big stars all around that. We are going to use that quite a bit when we think about torsion, figure out what the angle of inclination is and all of that. So that's one of our torsion equations. I'm going to use that to figure out what our second torsion equation is, right? So let's use this and let's just rewrite this a little bit. Let's put a line through there because that was the derivation of our first torsion equation. Now let's use this torsion equation in the second thing that we're doing. So I've got T over J equals theta times G over L, right? Everybody sees that. And that equals tau, my shear stress, divided by the radius, right? We've already figured that out. So if we simplify this a little bit, that's going to give us, let me just simplify this. I'm going to solve it for tau now. Tau is going to be G times theta divided by L times R. Right? In fact, I can extend that out, make sure R, is in the numerator. So that's my stress, G times theta times R divided by L. I shouldn't really put that the stress is that. I should really say that the stress, since the stress changes on the way out, right? The stress is 0 in the center. The stress is a maximum on the way out. So I should say that the stress really, if we were just finding it for any point along that line, would be G times theta times rho over L. So we could find the stress at any point in that cross section, right? Just by taking the distance from here to that point, we'll find the stress. The stress is always maximum on the outside. So if I wanted to find the maximum shear stress, then I would use rho, right? That would be the maximum shear stress at R, because R is the maximum distance from the center, right? And we can see that the stress, since it's a function of rho, is going to be 0 at the center, and it's going to be a maximum at R. So our maximum at R is going to be G times theta times R divided by L. Right? Does everybody see that? Okay. Now, if I were to replace G, theta, and L, right? We've seen that before. G theta over L. Where have I seen G theta over L before? Right? Well, if I go to this, G theta over L equals T over J, doesn't it? Let's just look at that. Let's just put this up here. So theta G over L, theta G over L equals, let's just look at this. Theta G over L equals T over J, doesn't it? So if I replace that with T over J, I get T R over J. Does everyone see that? T over J, and then R. R is still by itself. So maximum shear stress is going to be TR over J. If I wanted to find the shear stress at any point along here, it'd be T times rho over J, right? So this is our second torsion equation. Let's write that here. Tau max equals TR outer. Let's put outer because it's maximum, right? We want to make sure that everyone knows that we're talking about this R out here, not a random R, over J. Now J can change. J could be a J polar moment of inertia for a solid bar, could be for a hollow bar, could be for a thin-walled bar. And in fact, that is an example that I'm going to do. I don't know if I'll get all the way through that example in the next lecture because I'm going to do an easier example to start out with. But we'll see how far we can go to talk about torsion. Torsion is a very important part. There's three parts to solid mechanics. It's really uniaxial and shear stress, and then it's torsion, and then it's the flexure formulas. So we're going to do this thing, then we're going to get into the torsion examples, and then we're going to look at flexure. See you there.